So I remind you that you were supposed to watch the chapter on neural networks. So by now we already have. Remember we talked about hypothesis classes, right? So we had some parametric family of functions that serve as our hypothesis, both for classification and regression problems. We are talking about supervised learning. And now we have basically our workhorse. So we have a very rich class of parametric functions that we call neural networks, and specifically convolutional neural networks. And you saw also some of this stuff in the exercise now. So again, maybe I will just remind you some terminology that is admittedly is simply wrong in most signal processing books, but still it is commonly used. So I remind you that we defined, I denoted, I think, in the lectures by tau p. Tau p is what we call the translation operator. It takes a signal. A signal is just a function of, let's say, some multivariate variable, let's say an image, and it maps it to the same signal shifted by some amount p. Okay, so let's assume p is in our d. Let's say d equals 2 for an image. Okay, so we have two location coordinates, d equals 2, right? This is the dimension of the domain, and we are simply shifting the image by some vector p. Okay, so this is called translation operator, or shift, if you will. Okay. And now suppose we have a function. Suppose we call this function a system. At least in the signal processing jargon, it is called a system. Suppose we have a function y that takes a signal and gives it some output. Let's call it y. Okay. It can be a scalar. It can be just a scalar. It can be some other function of this variable x. Doesn't matter. Okay. Now, if we apply this system y to the translated version of our input, and as the result we don't see any difference in the output, okay, we call this property translation invariance. Okay, this is translation invariance. Invariance means that you don't see that your input has been translated. Okay. Now, if on the other hand you have, and of course this now I will make an assumption on the output of the system. I'm assuming that the output is also another signal on the same domain. Let's say now I shift the input, and the output will be essentially equal to first applying the system to the input f and then shifting the output. Okay, so it means that essentially that y commutes with translation, right? This is true for every f. So y commutes with the translation operator, and this property is called translation equivariance. Okay, and in the signal processing literature, these systems are called translation or shift invariant systems, which mathematically doesn't make sense, of course. It's a different property. Okay, so basically the building block of convolutional neural networks that we defined was basically a concatenation of layers, of convolutional layers. Every layer in its core has a convolution. Convolution is a linear translation equivariant system. Okay, so basically we first demanded that the system is linear. Linear means that it is homogeneous and additive, right? So if I have a system A that I apply to alpha f plus beta g, it means that I can write it like this. Okay, so this means linearity, right? So we first of all demanded the operation to be linear. Then we demanded this operation to commute with the translation operator. And as the result, we got this form of a Toplitz's operator that we called convolution. Okay, that was our building block. And there is quite an amount of theoretical justification that even if you want to get invariance, to obtain invariance to more complicated deformations, then doing multi-layer decimation or subsampling and convolution is a very good idea. So essentially, if you take, instead of this translation operator tau p, you take some more complicated deformation field that, let's say, has some bounded gradient, then you, by basically observing it in this multi-scale fashion by subsampling, by decimating the signal, at low resolution levels, you see a very coarse version of this deformation. And there are many computer vision techniques that have been using these properties before neural networks, before convolutional neural networks. Okay, but essentially we have this class of convolutional neural networks. We can think of them as our hypothesis class, right? So I have some function h theta. Okay, so this was our hypothesis. Let's say belonging to some family of hypotheses. Let's say this is CNN. Okay, theta is a collective name for all the learnable parameters, right? And now our goal is, of course, to do the supervised learning, right? So we have now specified this ingredient in our learning problem, right? So again, I remind you that our end goal is to compute some expected loss. Okay, this expected loss. So this hx predicts a label. This is our predicted label, right? Given the data. And we would like to see how distinct it is from the actual data. Of course, we compute this expectation on the joint probability of x and y, right? That is the setting. And we would like to minimize all this thing over h mapping from x to y, from the instance space to the label space, right? So that would be our end goal, right? So the only problem with this is that this object is not tractable. So instead of solving this problem, we are solving, at least we have no choice but to restrict our hypothesis class to this family of functions, right? So essentially we are minimizing the same loss, but over a different restricted family of functions. And I can, of course, rewrite it as minimization with respect to theta, right? We have a parametric family of functions. So this is a minimization with respect to theta of the same loss, obviously. Right? And this is your CNN, right? So basically all the complexity of your model goes here. This is your CNN or ResNet or whatever form of your hypothesis you elect to work with. Okay? But we know that we cannot solve this problem either, right? We don't have access to this distribution. We don't know it. So we cannot really compute this expectation. Instead, we take a finite sample, the so-called training set, and instead of minimizing the original loss, we minimize the empirical loss, right? So we have some big training set, and we are approximating the expectation by the empirical average. Okay? So this is what we are actually minimizing. So you see, we have basically every step we are making here introduces, well, this is just equivalent, right? So this is equivalent, but every step we are making here introduces some error, some amount of approximation, some amount of inaccuracy, right? So we need to somehow to be able to quantify this and to take it into account, right? So what you are going to watch next week will start with this setting. So there are different sources of error that are introduced by transitioning from what you would like to be able to solve to what you are actually able to solve. Okay, but then we are left with this problem. So let me write it again. We are minimizing over theta this loss function. Okay, let's call it L function of theta. Okay, so it is a very complicated function, but it is a function of theta because these are your degrees of freedom. These are the optimization variables. Now you can observe several things. So first of all, how the heck do you minimize it? What does it mean even to minimize this function? Now it also has, you see this sum, this number n can be very big. It might be simply impossible to compute this function end to end, or it might be extremely expensive to compute this function, basically to do all this sum. So then basically by maybe taking some kind of what is called mini batch here and not computing it on all the training set, and maybe by converging to something that is different from the arg minimum of the minimizer of this problem, you're going to introduce another error, right? Because basically you're running an actual optimization algorithm that will not exactly give you the global optimum of this problem, right? So there is another source of error that we are introducing. So again, we are going to discuss this in the video that you're going to watch. So you can treat it as some kind of a mini course on numerical optimization, really all the essential things that you need for our purpose, with emphasis on stochastic optimization. But I would like to remind you in this hour that we have, I would like to remind you some basics. And again, there are these are well-known notions. I also prepared a reference online with just a brief overview of these known notions, but I think it is still worthwhile to go over these notions in class because they are fundamental for what we are going to do. Okay, so essentially we are interested in minimizing a function over some n-dimensional variable. Okay, so we have a function that takes us from Rn to R. It's a scalar valued function of an n-dimensional vector valued argument. Okay, and we would like to minimize this function. So our tool that we are going to use for minimization is multivariate calculus. Okay, essentially differential calculus of functions of multiple variables. Okay, so let's first start with the one-dimensional case and then upgrade ourselves to the n-dimensional case. So in the one-dimensional case, the fundamental notion of calculus is the notion of a derivative, right? So let me draw a one-dimensional function. This is theta, this is L, okay? Let's say I have this is the graph of my function, okay? I will put some value of the argument theta here, and the value of the function L, okay? And then I'm going to displace my argument by an amount that I will call d theta, okay? And as the result, I'm going to be in this theta plus d theta on the horizontal axis. The function itself will change by an amount that I'm going to denote by delta L. Okay? And of course, the function can be very complicated. Its form may be very complicated. So what I'm going to do, I want to work with simple functions. So the simplest function I can imagine is a linear function. So I'm going to approximate my function with a linear function. So here goes a linear approximation. Okay? And the linear approximation, of course, it is not exact. So the linear approximation will change by another amount, okay, that I will call dl. Okay? And if I have a good function, a nicely behaving function, it will happen that delta L will be equal to dl plus some error that depends quadratically on d theta. Okay, so of course I should write it formally as a limit, but you see the idea. When this interval becomes smaller and smaller, if the function is nicely behaving means that it is differentiable, or C1. It means that I can take this d theta in the limit to 0, okay? And then the linear approximation that approximates me how the linear approximation changes will coincide with the actual change of the function, delta L, okay? And I can write this rate of change, dl over d theta, and call it the first order derivative of L prime at point theta. Okay, again, if this limit exists, if the function is not differentiable, this limit will not exist, this statement will not be true, and of course the derivative will not be defined. Okay, so this is the first order derivative, and of course an alternative way to state the same is by saying that if I want to get the value of my function at theta plus a small displacement d theta, I can write it as the value of the function at point theta, right? This is the value here, plus a linear approximation. Well, a linear approximation, obviously the slope of the linear approximation is this quantity, right? It is the first order derivative at point theta times d theta, right? It's a linear function, plus some residual that depends quadratically on d theta. And this is called the first order Taylor expansion, right? It is, you can think of it as an alternative way to define this notion of a derivative. So the mathematical object that goes here is called a derivative. Okay? I hope this is obvious. So if you find this obvious, let's upgrade ourselves to the n-dimensional case. In the n-dimensional case, we of course have theta in Rn, right? The function maps from Rn to R. And I will use that definition that usually goes under the Taylor's theorem. So I will use it as my definition of the derivative. And you can basically, you can show that the Taylor's theorem is sort of an if and only if statement. You can use it to define the notion of the derivative. So I will use it exactly in the same way. So L theta plus d theta, just now pay attention that this is a vector. You have displacements in every direction of your n-dimensional axis, right? So you have, it's a vector valued quantity. And again, it is the value of the function at the point theta plus, instead of having this product, I will have an inner product of two vectors. Let's write this inner product. Standard Euclidean inner product of something that generalizes the notion of the first order derivative and d theta as before. Okay? Plus a term that depends quadratically on d theta. Now remember, d theta is a vector, so I write a norm of d theta. It can be any norm, let's say the Euclidean norm. And the quantity that goes here is called the gradient. That is the vector valued version of the first order derivative. It is denoted by nabla L theta, or we will call it G theta as well. Okay, so so I will use this way to define the gradient. Okay. Okay, so for example, just a trivial example. If I have a linear function, let's say L theta, this is an example. Let's say it is equal to W transpose theta. The result is a scalar, obviously, right? So what would be the gradient of this function? So let's do it by definition. Let's do it by definition. So I will write L theta plus d theta as W transpose theta plus d theta, right? So it will be W transpose theta, which is nothing but L theta, plus W transpose d theta, right? So I'm getting exactly what Taylor expansion gave me. L theta plus what is written here is the inner product of W and d theta, right? So it's the inner product of W and d theta, and in this case I have zero residual because the function is linear, so its linear approximation is exact. And this object here is called the gradient. So you see this rule, when you take the gradient of some linear form, the gradient is that linear form transposed. It's that joint, right? The transpose. Okay, so this is the gradient. Okay, in the case of a linear function, the gradient is constant. Yes? So W in this case is a vector in Rn, and theta is a vector in Rn. The function is scalar valued. Of course, you can upgrade this to the, let's say, to a map that maps from an n-dimensional input to an m-dimensional output. And in that case, the typical name for a gradient is called the Jacobian matrix of the function. Okay, but it's exactly the same mathematical object. Okay. Now, this is how I would like to define the gradient. And if you accept this definition, I mean, you have no choice. You need to accept this definition. But if you use this definition, you can actually see how easy it is to derive gradients of complicated functions. Okay, so you can use this. You can follow this example for any function you like. Basically, the chain rule works exactly using this kind of. This is calculus of differential quantities. I'm not writing limits all the time, so I just remember that anything that has d theta to any power bigger than 1 is 0. Okay, so all quadratic terms in theta or any higher order terms in d theta become 0 because they go much faster than linear to 0 when I take the limit. So I don't write the limit. I just remember how to operate with these quantities. Okay, so this is what calculus is about, right? So we define the derivative with the limit, but then we forget about this definition. And of course, you remember that in the standard Euclidean basis. So let me just summarize what we've seen so far. We just wrote that dl, this is called the differential, equals to the gradient. Let's call it g times d theta. Okay, so this is called the gradient. This is called the differential. Okay, and this is the change of the argument. Okay, just remember that this g, this gradient, in the standard basis, of course, it is given as the vector of partial derivatives. Okay, in the standard Euclidean basis. Of course, in any other basis, it can be different vector. Any questions? Okay, so let me take our function. I can draw a two-dimensional function, a function of 2 arguments. Let me draw. These are the level line of this function. Okay, and let me draw some direction. Let's take a point x, or not x, theta 0. And let's take a direction r. Okay, so I take a direction, so I section my n-dimensional argument space along a one-dimensional ray or one-dimensional line in the direction of r. So as a result, I can draw a new function. Let's call it phi alpha, and phi alpha is defined as L theta 0 plus alpha times r. R, of course, is a vector in Rn, same as theta 0. Okay? So I selected a point, a direction, and I can now section my function in that direction and get a one-dimensional function of a single argument. Okay? And I can ask myself how much the value of the function, of the original function, will change if I make a small step in the direction r. Okay, so it looks like the definition of a derivative, but it is somehow related to that direction that I selected, and it's called a directional derivative. And the directional derivative is typically denoted as L prime r at point theta 0, and it will be simply given by the regular first order derivative of the function alpha, function phi of alpha at point 0. Or if you will, d over d alpha of phi at point alpha equals 0. Okay? And how do you express it in terms of the gradient? let's see it directly from the definition. So d phi, because phi and L is exactly the same thing in our case. So d phi, the differential of phi is exactly the differential of L, right? And dl, we know how dl is expressed, right? This is our expression for dl. Okay, so dl is expressed by the gradient. Let me continue denoting it by g. Of course, g means the gradient at point theta 0 times d theta, right? And what is d theta? Let's translate it into d alpha, right? So let's write it as g transpose theta 0 plus, well, I mean, theta 0, of course, doesn't matter, right? Because, well, so if I write theta as theta 0, or sorry, let me write it like this. So theta plus d theta equals theta 0 plus alpha r plus alpha dr, plus r plus d alpha r, right? So I care about this d alpha. So essentially d theta is d alpha times r, okay? And I get this quantity, I get g transpose r, this is the inner product of the gradient with the direction, times d alpha, okay? And this is the definition of my derivative, of phi, right? With respect to alpha. So I just divide everything by d alpha, and I get that the directional derivative, phi prime, or LR prime, equals to g transpose r. Okay, so this is how you can calculate the directional derivative from the gradient. So the gradient contains the information about directional derivatives in every direction. You just need to project it onto the appropriate direction. Okay, and we will see that there will be directions that along which the function decreases, and these are called descent direction, and there are other directions along which the function increases. And to do minimization, as you will see in the video, you need to go to descent directions, right? And one of the standard choices of a descent direction is the negative gradient. So if you go in the direction of the negative gradient, you get the steepest decrease in the value of the function in the sense of some norm, okay? And in other senses, you might get different descent directions that are better, okay? So you will see it in the video, okay? So of course, the main point here was just to remind you the notion of the gradient, and without limits and without necessarily working coordinate-wise. So we didn't do anything coordinate-wise here, right? So it was all defined as vector operations. Now let's go to the higher order. Let's talk about the two-dimensional, the second order derivatives, okay? So again, we are staying in the n-dimensional case, and we are going to the second order. Remember that we had a function L, function that mapped an n-dimensional vector to a scalar, right? And its gradient was given by this identity, right? So now the gradient itself is another map from Rn to Rn. Okay? So if you want to be completely formal, it maps vectors into covectors, okay? Or to linear maps. But you can think of it as something that maps vectors to vectors, n-dimensional vectors to n-dimensional vectors. At least for our purpose, it will be enough to define it in this way. And you can write it in coordinates, right? You can write G as a vector G1 until Gn. Of course, each such Gi is again a scalar valued function, okay? And if it is a scalar valued function, and if this scalar valued function is differentiable, we can write dgi as some other object that is the gradient of that coordinate of our gradient. Let's call it hi transpose d theta, right? And of course, let me write it from 1 to n, okay? Or, since I don't like writing anything in coordinates, let's write it as a in a matrix vector notation. So instead of writing dgi, I write dg, which is an n-dimensional vector. Instead of writing these h1 transpose until hn transpose, I will write here the matrix h, n by n matrix, whose rows are these hi transpose, times d theta. Okay? So we actually defined the gradient as the object that makes this relation hold. And in the second order, I'm saying that there is an object. If the function is differentiable twice, we call such a function C2. If it is differentiable twice, then this identity will hold, and the object that relates the differential, basically the differential of the gradient dg to the change of the argument d theta, is called, it would be called the second order derivative in the one-dimensional case, and it is called the Hessian matrix, or the Hessian in the d-dimension, in the n-dimensional case. Okay, so this H is a Hessian. It's called the Hessian. Okay, and a particularly nice property for these continuously differentiable functions to the second order is that the Hessian is a symmetric matrix. It essentially means, again, if we write it in coordinates, the Hij is the second order derivative, partial derivative of L at point theta with respect to d theta I, d theta j. And we know that if the function is twice continuously differentiable, then you can change the order of differentiation. You can first differentiate with respect to theta I and then with respect to theta j. So it means that, of course, Hji equals to Hij. Okay? Any questions? So this should be familiar, I hope, right? So again, we can write it as we did to define the gradient. We defined the gradient through Taylor's approximation. It was approximation to the first order. Let's do it to the second order. So it will be L theta plus the inner product. Let me write the inner product with the transpose. Let me write it as the gradient transpose with the theta plus, so we have a linear term, we have basically a constant term, a linear term, and we have a quadratic term. So the quadratic term, I will write it as 1/2 d theta transpose. Hessian is denoted by this nabla squared. This is the symbol for Hessian. It's differentiating twice. Or you can think of it as gradient transpose. L theta d theta. So this is a quadratic form. This is known in algebra as a quadratic form. Plus, of course, we have some additional term that will be of third order. Okay? So obviously, when d theta is small, this approximation is so much more accurate than the linear approximation. Okay? Now, you can also interpret this geometrically, and we'll talk a little bit more about it in the video. So what is written here is a quadratic function, quadratic in d theta. Okay, so this is a quadratic function in d theta. A quadratic function, it's basically it's a multi-dimensional generalization of a parabola. Let me draw some function of this kind. I can draw a two-dimensional function. Something like this. So this is our domain. Let's say this is a point. Okay, so this is a point theta. And I can select a direction. I can select a direction. Let's call it R, as we called it before. And along this direction, I will have some one-dimensional function. Okay, so let me draw this one-dimensional function. Okay. And now think of this object that the graph of the function creates, right? And let's put a vector that is perpendicular to the graph of the function. Okay, so I can put a tangent plane to the graph, and a vector that will be normal to this tangent plane is called the normal to the graph. Okay, so let me draw a normal here. Okay, So let me draw a normal here. Okay, so this is my normal. Let's draw it here. Okay, so I'm at some point. This is the normal to my graph. Okay, the normal always points outwards of this graph. Okay, and then I do a small step in this direction. Okay, so basically it's a small step in the direction r, and the normal also changes, it rotates, right? Now, what is the projection of this change of the normal? So basically the normal changed from this to this, right? Something like this. What is the projection of this change on my horizontal axis? So this is the direction of my step. What is the change in the normal? It is also pointing in the same direction, right? So the normal rotated in the same direction as I did my step, okay? And this is called positive curvature, okay? And of course, the amount of curvature tells me how fast my normal rotates. So you can think of if this curve describes the trajectory, for example, of a vehicle, then this rotation of the normal would correspond to the acceleration vector, right? And if I'm making a sharp turn, then of course the curvature will be high, and I will be feeling the g-force, right? I will be feeling the acceleration of my turn, right? So this is in this case this curvature vector points in the direction of the normal, and its length, its magnitude, tells me how curved my path is, how strong I need to accelerate to stay on the path. Okay. Now, if I draw another graph, let's say like this. So here I have a normal that, as you can see, rotates in the opposite direction. So I make a step forward, and the normal rotates backwards, and this is called a negative curvature. Okay. Now we know that the first order directional derivative is given by the projection of the gradient with the direction r. If we take the second order directional derivative, it will be given by this quadratic form r transpose h r. H is the Hessian matrix. Okay, you can prove it for yourselves exactly the same way we did it for the first order. It's exactly the same calculation, and it means that if you want positive curvature in every direction, what does it mean? If you want positive curvature, so let's say positive curvature for every r, for every direction. What does it mean? It means that this quadratic form r transpose hr has to be positive for every r distinct from 0. And I don't insist on the direction vector to be a unit vector. I just make sure that it is non-zero. And the algebraic property of a matrix that satisfies for every r this quadratic form being strictly positive is called positive definite matrix. Okay, so I demand that the Hessian, so these are if and only if statements, right? So the Hessian is positive definite. And another way to state that the Hessian is positive definite is by demanding that all the eigenvalues of the Hessian are positive. Okay? So the eigenvectors of the Hessian correspond to the principal curvature directions in which the first principal direction corresponds to the highest curvature, the last corresponds to the smallest curvature. And if we want positive curvature, we would like these eigenvalues to be positive. Okay. Now, why should I insist on positive curvature? Why do I care about positive curvature? Yes. So somehow this curvature is related to being at a minimum. Okay. And again, you will see in the video more details about it. But essentially, if you think about this shape describes a minimum, right? any point, if I'm staying at the bottom of this valley, any direction I will go, I will increase my altitude, right? I will increase the value of my function. And this shape is characterized by positive curvature in every direction, right? And if I for example, stand on the top of this hill, then every direction I will go will decrease the value of my function, and this is the shape that has negative curvature in every direction. And of course, I can have something that is called a saddle point, something like this. Sorry, pardon my drawing, but basically, I have this direction of positive curvature and this direction of negative curvature. Okay. And there is a geometric property that relates to positive curvature, which is called convexity. Okay. I'm sure it is well known. Usually it is defined in a horrible way, so I will try to give you a friendlier definition. So first of all, let's take some n-dimensional space. Let's say for our purpose it will be Rn. And let's take two vectors u and v coming from Rn. So I have a point u and I have another point v. Okay? So how do you mathematically define a segment, a linear segment connecting u and v? So you can draw this segment and just say a line connecting u and v, or a linear segment connecting u and v. But basically, how do you mathematically describe any point on this segment? So it's clearly it is a one parameter family of points, right? Let's call this parameter lambda. Lambda will allow me to move on this line. So I will say 1 minus lambda times u plus lambda times v. And lambda goes from 0 to 1. When lambda is 0, I'm at u. When lambda is 1, I'm at v. And anything in between are the values from 0 to 1. Okay? And if you want to sound smart, then you will call this a convex combination. Combination of u and v. Okay? This is called a convex combination. Now, if we have a set C in Rn, the property of being closed under convex combinations tells us that basically we say that the set is convex if it is closed under convex combination. So we say that this set is convex if for every u and v and lambda between 0 and 1, 1 minus lambda u plus lambda v is also in C. This means that we are closed under this operation of taking convex combinations. So for example, this set is not convex, right? Because we have 2 points, and some of the points on these convex combinations are not in the set. Okay, so it's not closed to convex combinations. And this set is convex, right? So no matter which 2 points you take, all the linear segments between them will lie inside the set. Okay. So what is the opposite of being convex? So the opposite of being convex is non-convex. Okay, there is no such a thing as a concave set. Okay. So let's extend this notion to functions. Let's extend this notion to function, and just again remember our object of interest is this function L from Rn to R. Okay, so its domain lies in Rn, and I will of course just remind you what is a graph of L. What is a graph of L? It's a set with in Rn plus 1, of course, right? It's a set of this form. It is a set of theta L theta, right? Theta in Rn, or if the function is defined on some smaller domain, then of course theta in the domain of L. And of course this is a set in Rn plus 1, right? So it's tuples theta and the value of the function at point theta. Okay, so the graph of a one-dimensional function lives in 2D, right? This is the graph. Theta and L theta. Okay, and I will define a set which will correspond to everything above the graph. Okay, so if we want to again to be smart, you write you say above in Greek, and it sounds like epigraph, the epigraph of L, and the epigraph is defined as theta L, theta from Rn, and L above L theta. Okay, so this is the definition of the epigraph of L. Now, you say that L is convex if the epigraph of L is a convex set. Okay, and this is the way you extend the notion of convexity from sets to functions. Okay, so this is, I think this is the cleanest definition of convexity for functions, instead of writing inequalities and saying that the function lies above the chord connecting between 2 points, or I mean below the chord connecting between 2 points. I think this is much cleaner. And you can say that L is concave. So there is no concave set, but there is a concave function. A concave function is a function whose negative is convex. Okay? Okay? And what is important is that if we have L that is C2, that is twice differentiable, convexity means that the Hessian has no negative curvature. Or actually, I will write positive semi-definite, because then you distinguish between what is called strong or strict convexity and convexity. So a convex function might have, for example, a convex function can have this form. Okay, so it can have a plateau. It's a convex function, but it is not strictly convex, and this is a strictly convex function. And for this function, you might have positive semi-definite Hessian, and for this you will have positive definite Hessian. Okay. What is important about convex functions, and I will finish here. So remember that at the end we would like to solve this minimization problem, right? And this problem in general is unsolvable. Just imagine how crazy can this function be. So how are you going to find its minimizer? It's the lowest point in this landscape. What is particular is that if L is convex, then every local minimum, something that you can describe by this shape, will necessarily be its global minimum. Okay, and it means that you can use local methods that make small steps based on local information. And by local information, I mean the value of the gradient and the Hessian. Okay, so this is local information because it tells how the function changes. It approximates the function for small steps. It doesn't see that, let's say, I'm standing at this point, so I think this is the minimum. So according to my local information, I'm at a minimum, but I don't see across that hill that there is another much lower point right here. So for convex functions, there is no distinction between local minima and global minima, and that's why they are so important. So essentially, we know how to solve these problems for convex functions. Okay, and what we are going to face in reality, for our purpose of these classes, that we are going to face very non-convex functions and optimization problems with very non-convex objectives, and we will see that without theoretical explanation thereof, we are going to be able to actually get useful and usable solutions. And there is no explanation, at least I cannot offer any sufficiently convincing and general explanation why it works. Some sort of black magic. It just tells me, at least I think I'm not the only one who believes this, that classifying problems into convex and non-convex is a very crude classification. It is very it is simply a manifestation of how imperfect and how primitive our analytic tools are. So there are non-convex optimization problems that clearly have global algorithms that guarantee global solutions. For example, if you want to find an eigenvalues or eigenvectors of a matrix, you can write it as a minimization problem that has a non-convex objective, right? It's just sufficient to see that if you're looking for an eigenvector, the negative of that eigenvector is also a solution, and convex objectives cannot have two solutions of this kind, right? So it must be non-convex, and still we have algorithms that give us global solutions to this minimization problem. Again, classifying the world into convex and non-convex, it was a very useful exercise that people did in the 60s, in the 70s, in the 80s, and the 90s. I think now when we are facing a class of problems that definitely demand non-convex optimization, we should look for better and more delicate analytical tools. Probably it is a philosophical question whether we are whether we want to to exactly solve models that have no connection to the reality, or build better models that we don't know how to solve, but we can try solving. Okay, and I think there are many revolutions, not only in this field, but in many fields that arose from the fact that we replaced some ad hoc, some pragmatic models that we knew how to solve and maybe had some closed form expressions, replacing them by models that we didn't know how to solve. And then, of course, it drove entire fields to give new tools for their solution. Okay, so I think we are still standing at this initial point of still lacking the proper analytical tools to understanding why deep learning works. Okay, but there is quite a significant evidence that it does. So again, we'll see numerical tools for solving minimization problems. They have no guarantee whatsoever. The only guarantee is that it will converge to a local minimum, but practice shows that the local minimum is useful. Okay, so then I will invite you to watch the video detailing all the numerical algorithms, and then in the next class I will discuss some things related to it. Well, see you next week.